Hi, everyone. I'm really happy to be here. I'm going to do a little bit of a dive into multi-material additive manufacturing, what it requires, what the challenges are, go a tiny bit into the chemistry of metals, but don't worry, I won't go too deep, and I'll be really big picture of explain what's going on. So we get on, oh, yeah, it's a clicker right here. Is there a clicker? Oh. Oh, perfect. So yeah, just a little bit about me. My name is Kuba Price. I'm a PhD candidate at Oregon State University. I focus mostly on the metallurgy of dissimilar metal welding. Specifically, I focus on the Inconel Girocop 42 joint. Here you have a BSD image, so each color represents a grain, which is essentially similarly oriented atoms. And then I also put this presentation together with my colleague, Stephanie Lawson, and she essentially does the CFD modeling of what I do experimentally. So moving on to the next slide. Why do we want to do multi-material additive manufacturing? And why do we want to go, as we'll see in this presentation, there's a lot of problems that can arise when we try to mix metals. So what do we gain from doing this? And I'd like to present a few case studies here. So we have rocket exhaust chamber developed at NASA. And essentially, if you want to make an exhaust chamber, you have a few options. You can make the whole thing out of tungsten, refractory such as tungsten. It's going to be very heavy. It's going to be really expensive. So another option is that you can use a nickel-based superalloy and put a copper-based interlayer inside. And if you put coolant through the copper-based interlayer, right there, you can kind of cool your assembly, and you've got a process. However, if you want that to happen, if you want to make a component like that, you've got to join the copper-based alloy to the nickel-based superalloy. Same thing with a superheater or a heat exchanger, right? So we want to decrease in entropy. We want to increase the efficiency of our heat exchanger. We want to use a more conductive material in order to transfer the heat between the hot and the cold flows. Another example, this is from paper I read, and from Washington State University. It's a concept for a medical implant. So a lot of times when you have a medical implant, you have essentially a ball joint, and you have a component that connects to a bone. Usually these components are made of titanium. Titanium has a similar modulus to bone, so it's kind of compatible with medical applications like that, but we get a lot of wear with titanium. So if you, for example, use a cobalt, chromium, molybdenum ball bearing, you can kind of reduce the wear. So again, if you want to make this happen, you have to join that to the titanium. So how do we go about actually making these components, right? So we want to produce it, for example, and we've seen a lot of here powder bed fusion. It's very progressed. We've seen that at Formnext here, right? That there's a lot of LPBF parts being made. So if we actually want to make this using LPBF techniques, right, we're going to recode, and then we're going to build up in the Z direction. Now, it's not very hard to change your material if you actually want to just change your material in the Z direction. So you want to deposit, for example, different material here, down here. But if we want to do it in plane, right, we're recoding a single material. If you want to do it in plane, it's more difficult to create a multi-material part. It's kind of two basic systems that have been developed, two mindsets for how to do this, versus a vacuum-based system. So in a vacuum-based system, we're going to lay down material, then we're going to expose, and we're going to vacuum up that powder, and then we're going to deposit a different powder, expose again. So that's kind of one method that's been developed, and a number of companies are looking at that. And then another mindset is to use a selective recoder system. So in this case, we have a recoder that's actually able to selectively decide where to deposit what powder. So there's actually a company in Belgium called Aerospace. They've integrated their multi-material recoder with a quantity machine. They've really been able to make some beautiful parts. So the technology is actually quite developed on LPBF with these multi-material parts. And then if we move on to DED, it's actually less of an issue. So again, we don't have this, we're essentially extruding or putting out our material from the same source as our energy, as what's actually melting the material. So we actually have a higher amount of multi-material parts that are made. But what's really stopping this from industry acceptance, what's really stopping this from being used, are the metallurgical constraints. And that's what I'm going to discuss in the next few slides. So what happens? How do we have to kind of shift our mindset when we talk about multi-material? First thing I want to introduce the audience here is the fact that we're going to have shifting boundary conditions when we use multi-material additive manufacturing. Okay, so I think, at least I used to work in aluminum manufacturing. So we had one parameter, and that was our golden parameter. And we would print with that, and you never changed it. The assumption there is that if you use the same parameter, you're going to have a similar cooling curve. And by that, I mean you're going to have a similar max temperature, you're going to have a similar cooling rate. And hopefully, you hope to get your cooling rate and your max temperature such that you're not going to get any defects. That kind of goes out the window when we talk about multi-material additive manufacturing. So if you're, for example, depositing a nickel-based alloy on a copper-based alloy, that copper-based alloy is just going to suck all the heat away. And I actually have this simulation here to give you guys some extent of what's going on. So here's a single parameter. We're depositing that on top of a nickel alloy. The same parameter on top of a copper alloy. Look how much smaller the melt pool is. Right? So one of the things you have to do is you have to adjust your parameters. So if you want to, for example, avoid this lack of fusion that's happening due to the high thermal diffusivity of the copper alloy sucking that away, you have to turn up your power. So you're actually in the first layer, we turn up the power to 800 watts, remove that lack of fusion. But again, just getting out of this mindset of the parameter needs to be kept constant. That's something that we kind of just need to forget about, unfortunately, if we want to really get into this multi-material. Now I'm going to talk a little about the chemistry that can happen when we do multi-material additive manufacturing. And if we're using a liquid state process, what's going to happen at the interface is you're going to get mixing. Say we're putting a copper alloy on top of a nickel-based alloy. There's going to be remixing of the bottom layer, and you're essentially creating a new alloy at that interface. Okay? And there's a number of things that can happen. A lot of them are alloy specific. There's two main things I want to talk about here that are actually, it's kind of a general problems that we can have. And that's solidification cracking and cracking due to brittle phases. So right now, just do a little bit of a dive into solidification cracking. So solidification cracking occurs, and first I want to introduce this concept that when we mix two metals, when we have an alloy, you're going to actually have a range of melting temperatures. So of course, water freezes at 0 degrees Celsius, but if you have a copper-nickel alloy, for example, there's going to be a temperature at which it begins to solidify, a temperature at which it ends to solidify. Solidification essentially ends. The top one's called the temperature at which you first start to solidify is called the liquidus. Temperature at which you finish solidifying is called the solidus. The bigger that temperature range is, the more likely you are to have solidification cracking. And lucky for us, what we're actually able to do is we're able to use thermodynamic software and predict what this temperature range is. So, for example, we have a phase diagram here between copper and nickel. Here we have kind of a lower. So this zone right here shows this temperature range for each composition. Here we're at 50%, for example, 10% nickel, 50% nickel. Right? The bigger that temperature range is, the more likely we're at to solidification cracking. So here, I would expect there to be a higher solidification cracking coefficient susceptibility than, for example, there. And there's other methods to do this, but this is just a general intuition we can develop. And we have, for example, brittle phase formation. So if we don't have the solidification cracking, what can happen is we can form these ionic type bonds. So they're called stoichiometric compounds, but it's basically what's happening is instead of having these beautiful, for example, face-centered cubic pure copper or copper-nickel mixture that's phase, essentially, what is occurring is we can form these compounds that are, in this case, we have a copper aluminum, we can have Al2FC. So these are almost ceramic type, ionic type bonds, and they're very brittle. And what can happen is when we're mixing, for example, we have a copper-nickel joint and we're mixing. If we mix somewhere in between this range where you see all these green lines, you can precipitate these phases, and those can cause cracking. So again, we can predict, lucky for us, we can predict this using thermodynamic software, but this is what can actually occur at that interface. So a case study on some of our work that we've done at Oregon State University, GRCOP 42, Inconel 625 joints. And this is kind of to highlight to you guys, yes, we talked about solidification cracking. Yes, we talked about brittle phase formation. But a lot of this stuff can also really just be material system specific. So if we're talking about a system such as Inconel 625, GRCOP 42, these are both alloys. So Inconel 625, quite a bit of chromium. What we found actually is that there's a liquid miscibility gap that occurs. What does that mean? What that means is that in the liquid state, we're almost like oil and water. We're getting this copper-deprived, copper-rich liquids that are forming. So you can imagine, for example, I don't know, melting butter in a cup of water or something like that. And what we found is actually this liquid miscibility gap, and it starts around, if we remelt and we have a liquid composition that starts around 30 weight percent GRCOP 42, goes all the way to almost pure GRCOP 42, we found that this lack of liquid state mixing occurs. And that can actually result in a solidification cracking type phenomenon. And the compositions here, so from about 30 to 50 weight percent GRCOP 42. And if we go from 50 to about 90 weight percent GRCOP 42, we can get a lot of brittle phases. So this copper-deprived liquid will separate out, and it will form some brittle phases that result in cracking. So right here we see cracking. So again, yes, we can introduce some general concepts as to where to predict failure, but again, it's very material specific, and if you're joining Inconel 718 to, for example, aluminum, you could have a whole other set of failure mechanisms. So where does this all take us? What really needs to happen for industry adoption? Because there certainly is a motivation, and there is a future in multi-material additive manufacturing, right? We want the design freedom, both from the geometric perspective, but also from the property perspective. We want to be able to lay which property we want, and in order to really do that, we need multi-material additive manufacturing. And to do that, I want to introduce to you guys this concept of a control stream to avoid lack of fusion and keyhole defects. Okay, so I'm going to introduce this. Let's say we have a nickel-based alloy. We're depositing on a nickel-based alloy substrate. And we put a thermocouple. Right? If we don't use enough power, we're going to get a low peak temperature. We're going to get a low cooling curve. And essentially what's going to happen is we're going to get lack of fusion. And let's say these red lines represent kind of a tolerance or a boundary of where we're not going to get any defects. Same situation. Right? We increase our power, and we increase it by too much, we're going to get keyholing porosity that forms. And it's not going to be a robust material. So there's essentially what I want to introduce here to the audience, right, is that there's a window of parameters or of cooling curves where we're not going to get any defects. So take that same situation. Now we're depositing a nickel-based alloy on a copper-based alloy. Right? If we use the parameter that previously gave us a defect-free part, well, we're actually going to get a lower peak temperature, right? Because now we're depositing on a copper-based alloy. It's diffusing all the heat out. So the idea is that we have some sort of dynamic parameter adjustment, that we identify a window where we're having no defects, and then we automatically, some sort of closed loop controller or something, are able to aim for that and are able to essentially adjust our parameters so that we're aiming for a cooling curve. So what else needs to happen? So we discussed kind of the parameter adjustments that need to occur, helps us avoid lack of fusion, helps us avoid these process-induced defects. Another thing is a library of transition metals. So a lot of the times when we have these brittle phases, incompatible metals, chemically incompatible metals. So here, for example, we have iron, copper, they're insoluble. And that can lead to a number of issues. Let's say we want to join these for some sort of application. What we can do is we can actually introduce an alloy in between the two that serves as a transition composition. And this is kind of known in welding as a buttering layer. But again, for example, we saw here before, we have insolubility when we have iron copper, right? So you see all the green lines essentially indicate insolubility. We have no issues if we go from iron to nickel to copper. So it's like avoiding that issue, a little bit like a sandwich. And one thing I really want to highlight here is that whatever we introduce in the middle, it cannot have a lower yield than the two metals you're trying to join, right? Because if you introduce something that has a lower yield, now you've introduced the global min, you're likely going to get failure there. So you're no longer really using the benefits or the benefits of both the metals you're trying to join. And again, what else needs to happen from a chemicals perspective? So we talked about using a transition composition. Another thing we can do is we optimize our remelting. So I discussed previously some of our work on Inconel 625G or COP42. So again, we have this liquid miscibility gap, and actually if we kind of remelt in this range, we're going to get a lot of cracking at our joint. But if we optimize our remelting and remelt where we have no liquid miscibility gap, so here we only have the dark gray, we don't have two liquids, so each color represents a liquid, we actually get a robust joint. We don't get any cracking. So if that, yeah, anybody has any questions, here's some of my contact information, and Stephanie's. She does a lot of the modeling background of this. And with that, thank you everyone for coming. And that's all.
Thank you very much. Any questions? I can bring you the microphone. Such a comprehensive presentation that has left no questions in the audience. We have a question. 1 second.
Yeah, thank you for the presentation. Have you looked into DED, multi-material as well, or have you only used laser powder bed fusion?
Actually, all of our research is on DED.
Okay. Have you seen the same challenges with the transition for DED?
I mean, you're always going, if you have any sort of remelting, so if you use a liquid-based process, you're going to get some of the challenges that result, like that solidification, cracking, brittle phase formation. You can even sometimes get that if you use a solid-state process. What we have found is that a lot of times we'll have different sorts of failure mechanisms if you use LPBF versus LDED. That also has to do with the cooling rates of the two processes.
OK, thank you.
Yeah. You might want the mic.
One sec.
Have you encountered any challenges during the post-process heat treatment, and any ways to reconcile that?
So we haven't looked into post-process heat treatment, mainly because specifically what we work on is Inconel 625 and GearCop 42, and both those do not require heat treatment. If you use something like Inconel 718, you would need heat treatment. And yes, that's an issue that we've definitely thought about. There's a number of ways you can get around that. You could, for example, heat treat before you join. You could also, yeah, you'd have to optimize your heat treatment in a way to not introduce brittle phases. And of course, you can use thermodynamic software, but that's, again, another issue. That just increases the complexity. It's a good point, yeah.
Anybody else? I have a quick question. You say we need a library of the transition metals. But who will produce that library, or who needs to be involved in making that reality?
So I think what the future is looking like is there's going to be some sort of industry-driven applications. I think right now everybody's kind of afraid to touch it. And there's going to be people who are going to say, OK, we really need to connect 316L to, for example, copper. And there's going to be some sort of industry-accepted transition composition that occurs, hopefully comes from academia. And then, for any of this to be accepted, we all understand, it was just at ICAM 2023, and the big thing there was qualification. So we can print a lot of stuff, and we can make some beautiful parts, but how do we qualify it? And the way I see it is this is going to go, we're going to print it, we're going to develop the thermodynamics, we're going to be able to actually manufacture it, come up with the parameters, and then a few years of testing is going to have to occur for this to actually be used, and like creep, tensile, everything. And then hopefully that becomes the industry accepted way to join the metals.
So you're going to be busy for a little while yet then? Thank you very much.
Yeah.
Thank you.